A lot of times nowadays, when people talk about artificial intelligence, what they're talking about is generative AI. There was very little interest among business leaders until recently when generative AI hit the market in the form of ChatGPT. So we're going to have a unit now on generative AI. This is brand new. I didn't used to do this, but I thought this was important enough to address. So in this first lecture, I'm going to talk about how generative AI is the kind of the third paradigm of artificial intelligence. Um, you know, as I said, when Governor Youngkin decided to ask all of the state agencies to enumerate all of the artificial intelligence that was happening on their campuses, he wasn't thinking about machine learning algorithms, and he wasn't thinking about expert systems. Specifically, he was thinking about generative AI. So I think it's safe to say nowadays, when somebody says AI, they're talking about generative AI. So they're talking about things like ChatGPT and Copilot, Stable Diffusion, DALL-E, Synthesia, Midjourney, and Gemini now, which is really interesting because that's Google's kind of multi-format AI. Um, so these things kind of are very exciting. I recently read a paper that said that there has never been a technological phenomenon that advanced so quickly as AI has in the last 5 years and has generated so much excitement and interest. So, so generative AI really represents a new paradigm. It's the third paradigm of artificial intelligence. So I want to talk about, well, what are the other two? So back in the 70s, so first of all, yes, they were talking about artificial intelligence in the 1950s, but it didn't really go very far. It kind of stayed in a few computer science departments, math departments. And the first serious attempt to try to get computers thinking like people were expert systems. And we're talking about the 1970s and 1980s here, where they were considering the way computers could do something besides just computation. And the idea was, why don't we let a computer do what an expert does? So we have all of these experts in the world, everything from doctors to auto mechanics and artists that know how to do certain things. They have certain expertise. Is there a way that we could take all of that expertise and then put it into a computer? And these were expert systems. And the design of these expert systems really consisted of three components, where the expert would populate what's called a knowledge base, which is a database that has, okay, everything you know. Let's take the case of the doctor. The doctor puts everything that he knows into this knowledge base. Well, it isn't just facts that a doctor knows how to do. A doctor also knows how to look at new cases and then make inferences from those old facts into new cases. So there needs to be some kind of logic built into this system that starts with the knowledge base, takes in new information, and then reasons about it. And so these parts of the system were called the inference engine. And these were mostly written as if-then statements. So if the patient has this, and the patient has this, and the patient has this, then it could be this. So this is what inference was in these systems. And then the third component was the user interface. So the user was just a non-doctor, would query the expert system through the interface and then get back advice that's based on the knowledge base and the inference engine. So they built, a few expert systems, never really made it big into the mainstream. They were too difficult to use and too rigid. It took too much time to train them. So these were just it was an interesting bit of research, but never really caught on. So the next big step, now we jump ahead to like the 1990s, was machine learning, actually even 2000s. So machine learning took a whole new way of thinking about what artificial intelligence was. And as you know, machine learning, particularly supervised machine learning, takes labeled data, learns how to map the labels to the data, and then is able to take in new data and make a prediction about what that is. So if we have a bunch of pictures of lions versus mice, and it learned versus dogs, and the model learns how to differentiate between them, we put in a new picture and it tells us what it is. It tells us it's a lion, or it tells us it's a dog. So this turned out to be of limited use until computing power and algorithms advanced a little bit further, because these took a long time to train with existing compute. So machine learning got us pretty far, but then accuracy kind of stalled. And so the next big step was what I'm calling paradigm 2.5, which is deep learning. Before I get into that, I just want to review a little bit about what machine learning is and how it led to deep learning. So remember that what machine learning is it's basically just learning how to take input variables and calculate the value of some output variable. So in this case, let's say we had this data set and we wanted to be able to put in all of these variables. So, servings per package, ounce per package, total fat, carbohydrates, saturated fat, cholesterol, etc. So we wanted to be able to put all these in for some new data and then predict how many calories would be in that candy bar. So the inputs then are all of these things, and the output is calories. And the form that this took was just like a regression equation, where y would be our output. So this would be calories right here, and each of these x's is each of those variables. So serving, so we say total fat, saturated fat, cholesterol. So we've got all these x variables, and what we have to do is just come up with the values of these. So as long as we know what these betas are, then we have an equation where we just plug in all of our input x's and we're able to get back our calories. Okay, so the challenge here was just to learn the value of these so-called parameters. In this particular example, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9. So this would involve finding 9 parameters, each of those weights right there. Okay, and all right, so this is how linear regression worked, and this is like the basis of machine learning too. So let's imagine that we take this whole thing. In fact, I did this very thing. I turned this slide sideways so that now we have the inputs going into the left and the outputs actually are on the right. And now we have something that looks similar to what became known as neural networks. Or in this case, it's a perceptron, because it's only one level. But it's the same concept, where we just have these input x's, and each of these is an input x. And we are going to add them all up, so that's what we're doing with this equation, and then we're going to apply some function to them. We didn't do that before, but that's not a huge deal. We could just apply some function to them and get our output. So just like this. So now the challenge is to come up with these weights right here. Okay, so these weights are the same as these. Well, actually, let me fix that, because this one is actually that one. This one is this one. This one is this one. Okay, so once again, the challenge is just figuring out, okay, we've got our outputs, so in our training data, we've got our outputs, and we've got our inputs, and we just need to find out these weights. And we needed efficient, fast algorithms for how to find out what those weights were. Okay, so this was the beginning of neural networks. And here is just a slightly different picture of it. Again, it's just a math equation. It's nothing more than what we saw before. So this is adding up all of these x times w's, or x times beta, and then we're adding something, we're applying a function, and this is how we're calculating our output. So what we have to do is find all of these. And so this is just another way of visualizing what's going on here. So with machine learning and with deep learning, all we did is we had an equation that could take some inputs, figure out the weights in order to get to the outputs, and now we had a model where if we had a new input, we just multiply and add all those weights, apply that function, and boom, we have our output. So this is, so this is these were the feed forward neural networks. Again, we have our inputs on the left, and all that's happening here that's different from here is that we're adding a layer. So we have our inputs, we have our outputs, and now we're just imagining that there are these hidden units. So that gives us a couple more, a couple more stopping points, a couple more transitions along the way to the output. So we're learning a lot more weights. Each one of these arrows is a weight, and we just have to learn a lot more weights. But what happened was these kinds of, adding all these hidden layers and then coming up with much more weights, these wound up being much, much more accurate. And it was just astonishing. So we don't need to just have one output. We can have multiple outputs then, because all we have to do is just extend this notion of just having all these units and then having all these different weights applied to each of these. So in this case, this is what the neural network looked like that predicted the MNIST handwritten numerals classification problem, where they took in, I think it was a 16 by 16 picture, pixels. So the picture pixel data were the inputs. They ran it through a couple layers, and then each of these, so there are 10 different outputs, and those wound up being the probabilities of that. So what they would do is if this was the highest probability, then that was the number. So during your training, you would just set this equal to 1, the rest of these equal to 0, and then figure out what the weights would be, so that you could have a model to predict any new ones. Okay, now, so if you can have any number of inputs and any number of outputs, this is almost everything that we need to do any kind of data on the planet. So think about this. What we can't do here are sequences, right? Because all of these X's, so all of these pixels, for example, exist in the same picture at the same time. So some kind of sequence data like language or audio or video won't work with this. Well, it turns out that there is a certain neural network architecture that can handle sequences. And it's one that's used in Google Translate, right? So language is a sequence. So we have, a sequence of words here, and we are trying to output another sequence of words. So we're taking a sequence of words and figuring out how to output a sequence of words. So this is the new paradigm. So instead of simply predicting a label and outputting a label, so basically a classification problem, we can now bring in a sequence and generate a new sequence. And that sequence can be of any length. So any kind of speech coming in could be converted into a speech in another language using what's called a recurrent neural network, which we saw in the deep learning unit. So you've got this, this is how they are pictured. This is how they're typically written down. But the idea here is, once again, you have an input, and then you have a hidden layer, and then you have an output, right? So this is the word that comes in. So we have these different time stages. If we unroll this, notice this recurrent arrow here means that we now have a weight of this hidden layer going into itself. So the way this works in reality is you unroll it so that, this is the first word, it comes in, and then you try to predict the output word. This is the output word. And then the hidden layer has to have some weight in order to remember sequence data going on to the next layer. So this is word 2, this is word 3, this is word 4. So the reason why this is such an important insight is we now have architectures that can take in any kind of data, and they can output any kind of data. So if you want to input a sequence of words and then output pixels, as long as you can train a neural network to learn the weights for translating this sequence of words into these images, then you can do it. If you have a sequence of audio frequencies and you want to train that if you want to train a model that would take that input and then output written text, you could do that. It's a sequence going into a sequence. So this is really the key insight behind generative AI. We're no longer in the realm of just machine learning where it says, tell me what the output label of this is going to be. You can input any data and then just generate whatever kind of new data you want that would be appropriate for that input. So in the case of ChatGPT, you are inputting in a sequence of words, it's running it through its model, and then outputting a sequence of words. So this is really, the heart of generative AI. And the key insight is as long as we have enough data and computing power, and there are a handful of companies that do, we can build a model that can take any kind of data and transform it into any other kind of data. So while it looks like what ChatGPT is doing is it's just magically thinking and then coming up with an essay answer, really what it's doing is it knows how to take input sequence of words and then output another new sequence of words of arbitrary length. And I'm going to get into how that works in more detail in the next video. But so you can take text and then convert it into other text. So this is what ChatGPT does. There are now lyric generators where you can type in, write me a song about this, and it'll generate some lyrics for you. There are ways of converting a sequence of words into an image, and this is precisely what DALL-E does. If you've played around with that, you say, show me a picture of somebody on a horse, and it can do that. It's really just taking text data and then creating image data. You could take an image and convert it into text. These are the caption generators. These are astonishingly accurate because, again, it's just training data. If you have images and captions, you can learn a neural network, learn the weights that will map those appropriately. And you can also take text and have it convert into audio. So there are these AI music generators where you can type in, write me a song that sounds like this, and it will take that text and then convert it into audio. So if you think about it just as models that know how to convert one kind of data into another kind of data because they are trained to do that, I think these generative AI tools seem a little bit less mysterious. It's just one data format to another data format. Okay, so what we're going to see in the next few videos is, the data types that can be generated. You've seen text and you've seen images and audio and video. Well, I'm also going to show you that it can generate code really well. So for those of you who maybe write SQL or Python, this is really going to be a game changer because the code generation is so accurate, and I'll demonstrate that in a later video. But it also generates, again, it's just taking one kind of data and producing another kind of data. Scientists are using this to produce things like DNA and proteins and molecular structures. So they train, some kind of input data, and to map to some kind of output data, and it can put in some kind of new data and generate new protein structures. Now, this helps them understand them in some way. I don't know enough about the science to figure out why they need those, but they apparently do, and they're very useful. Another interesting thing is that it can take data, so structured data, just like structured data like this, and generate new data. So structured data to structured data is still just generation, but it can take this data and then produce a new data set that's got 1 million rows and roughly follows the same distributions as these. So it's plausible data, drawn from the same population. And so this enables you to have really large, robust data sets that you can then do other kinds of machine learning with. So the structured data to structured data is another kind of neat thing that generative AI can do. Okay, so in the next few videos, I'm going to show you specifically about large language models and how those work. And then I'm going to say something about images and code And then I'm going to wrap up with what I call technical foundations. Specifically, there's a neural network architecture called the encoder decoder or the transformer that really kind of enabled all of this magic to happen. And that will be optional because that's kind of technical. But for those of you who want to get into the weeds on that, I'm going to show you that.